Streaming. We're live from Sauk Rapids Rice High School. Welcome to BC Calculus.
Yeah.
All right.
Woo!
All right. So this is the last part. We're talking about basically parametric equations, polar graphs. Which, if you take a look, your input was an angle, so that's kind of like parametric equations where you could define x and y based on a sine, a cosine, and an r value. So this, I came up with some pictures that I think are pretty good. A vector in mathematics is a geometric representation that has two important parts. One, it has a length. So it doesn't go on forever like a ray. This starts at P and ends at Q. That length is called a magnitude. And it can represent speed, it can represent force, it can represent weight, it can represent some type of fixed quantity. The angle in which it is going with to the horizontal, so that's the other component. So it has direction and it has length. And this vector right here that's called V, and this vector right here that's called U, are equivalent. They're not in the same place, but they're equivalent because they have the same length or the same magnitude, and they're at the same angle to the horizon. They're parallel. Okay? So this is kind of, I call the original vector, but if I could take that vector and slide it anywhere I want, it's the same vector. It has the same impact on another vector. Okay? Vector valued functions. So the function here is going to be called R. And this is how we write a vector. This is going to be some number. And this is going to be some number. And it's going to be computed as T. And common way you see this, like this one up here. Let me put these notes in here. This vector right here, this vector V, which I write like that, could be written in this form. Or it could be written in this form. They're equivalent forms. And I'll talk about I and J in a second.
Is that a J?
This is an I, and that's a J.
What's that?
Oh, J's go like that.
She was actually right. It's actually. I was
Done.
Is a J backwards?
Really? J's don't go like that, huh?
No.
So that's not how you spell Jack?
Upside down.
That looks like laugh.
That says
A
laugh.
weird thing on the top.
I bet you spell Jack this way.
Yes.
Yeah.
Oh, okay.
Draw 3, Kruger. Now draw 3 upside down.
That's
That's backwards. Upside down.
You just do it a flip.
No, that's a regular.
Yeah.
Now look at your door.
They look like this.
No. Because you see, like,
It's okay. Let's just do the
Yeah, we got to keep going on. All right.
we kind of
Flora.
got off topic at the beginning, but like
Are we ever on topic?
smaller,
That's true.
bigger, you know?
I don't think so. All right, so
Wow.
I came up across this good explanation. It says, in an xy plane, I and j represent what are called standard unit vectors, which means you'd be going 1 unit to the right, and this would be you'd be going 1 unit up. A vector can be thought of as a line on a road map. There are usually several ways to describe the route, and I drew this particular route in. It says, telling someone to get from the beginning to the end, you could say go 5 miles at an angle of 45 degrees. This direct route is the vector. In this case, 5 is the magnitude because that would be the length of the route going that way. And 45 degrees is the amplitude or the direction. So that angle measurement is called amplitude. Often when we travel, we cannot go along the vector. You may have alternate directions, like go east 3.5 miles and then go north 3.5 miles. So you would go in this direction and then you would go in this direction. So this vector could be visualized as the sum of these two vectors, or 3.5i plus 3.5j. So I have 3.5 unit vectors in this direction and 3.5 vectors in this direction, or 3.5 miles in one direction, 3.5 miles in the other. The directions are broken into components. The I component is the horizontal or the x-axis direction, and the j component is the number of units in the y direction. The vector is the hypotenuse of the right triangle. So 3.5 squared plus 3.5 squared, if I took the square root of that, is really close to 5. And so that's the way that you compute the magnitude or length of a vector. You use the Pythagorean theorem. Okay. All right, next page. Example, how would we figure out the magnitude and amplitude of this vector? Well, the way I write this is I write these, this means the amplitude of vector, or excuse me, the magnitude of vector v. How long is that particular vector? And that would be equal to the square root of what?
12 squared plus 5 squared.
12 squared plus 5 squared, which is equal to, does anybody know 12 squared?
44.
13, very good. Okay, so this would have,
Pythagorean triple.
yeah, that's Pythagorean triple, yep,
Look at you.
yeah.
Look at me.
Okay, so how would I figure out theta here?
Sine.
You could do the sine what?
5
Inverse of what?
over 13.
5 over 13. You could do also what? Cosine inverse of 12 over 13. And the most popular way would be the tangent inverse of 5 over 12.
Why would that be the most popular?
Because those are the two things you're given. Okay? You don't have to do it that way. You don't have to then compute the magnitude.
That shows how big amplitudes are. The amplitude of
Okay? You will be asked,
No, but I don't know how.
pardon?
I said, when it comes to like vectors, what's the difference between the magnitude and amplitude?
Amplitude is this angle measurement.
Okay.
Amplitude gives us direction. So when we say like 45 degrees or pi over 4, that's with the horizontal. Okay, Abby?
Okay.
Okay. And then if the magnitude is the length of the vector, in the how far we've gone in that direction. Okay? All right, you will not have to do the next 4 things. Okay? That's not part of the what you can be tested on AP. But again, this is review. And so let's say I have a vector here, vector A and vector B, and I am together. This is what it would look like. Okay? Physically, you may have done something like this. Let's say you have this vector, and this is vector A, and you have this vector, this vector B. This right here would be vector C. This would be what we call the resultant. So if vector A was 3, 4. Oops, I got to write it like this. Which means I have 3i plus 4j. And I have vector B, and that's equal to 2, 5, which is 2i plus 5j. Vector C would be 5i plus 9j. And what happens there? It means whatever is, that vector grew. It got bigger, right? Now it could also get smaller. But in the case that I have here, we have a bigger vector. You can multiply by a constant. So let's say, again, I'll have vector 3, 4. And let's say I multiply that by 5. That's going to be vector 15, 20. And that's called scalar multiplication. A scalar is just a single number you're going to multiply by. Again, you won't have to do these. There's something called the dot product. And the dot product is this. They call it the dot product because this is, there's two ways to multiply vectors. One is called the cross product, and one's called the dot product. The dot product uses the dot for multiplication. The cross product uses the letter X for multiplication. And if you take a look, this means that you would find the magnitude of A, you'd find the magnitude of B, you know the angle between them, and so the magnitude of A times the magnitude of B times the cosine of that angle is what we call the dot product. And this value can be 0, negative, or positive. And it's the sign of that value that tells us the direction of growth, how does it compare to the original vector. We use this a lot in 3 dimensions. And again, you will not need to do that in this class. I just want to make sure, bring out some terms. My guess is maybe in physics you added vectors, maybe he had you draw them using parallelograms. I don't use a parallelogram, I just use a triangle. Because you end up drawing the diagonal, am I correct? Okay. The cross product looks like this. Again, you need to know notice the X here. You need to know the magnitude of A, you need to know the magnitude of B, you need to know the angle between them. And then you're just going to take those two magnitudes and multiply it by the sine of the angle. Hello? Yep. Yep. Can I get back to you? Oh yeah, I'll let you know before I leave. Okay. Okay. All right. All right. And the cross product, you take a look and, you know, so one of the things that is really interesting about math when you get to upper math is when you talk about multidimensional space. I don't know if you ever taken a look at that. Do you guys know anything about Einstein's quest for the unifying theorem? Okay. Can you explain to me what you know about the unifying theorem?
He was trying to figure out a constant that correlates his theory of relativity and something else.
Yeah, you're really, really close.
Gravity?
Well, to me, it was, here you have this molecule and atom structure, correct? So you have things that orbit right? When you take a look at a molecule, and you have orbits out in space. So these laws over here should be somehow applicable to the laws of atoms and such.
Wasn't he trying to like figure out an equation that worked for both small stuff?
Correct, exactly. That's the unifying theorem. You can do it if you look at multidimensional space. Our space is 3 dimensions. So there is a certain belief by mathematicians that there are more than 3 dimensions, and there's existence in those dimensions that we're not aware of. And if you ever want to really a good book that talks about that, it's called Hyperspace. And it's the idea, he starts out with, how is that even possible? Well, he talks about if you have a pond in which you have fish, the fish don't know you exist because you're not in their environment, correct? You're outside above that environment. And then he goes through, the author goes through and explains what the current thought is about multidimensional space and how mathematically we believe it to be true. Yep.
What is the theory that like if we're not observing something, we don't know it's there? What? Quantum physics.
Right. So right, that's this particular type of idea. And so when you talk about these vectors and everything like that, that's where the vectors are highly applied, especially the cross product and stuff. Again, we won't be doing these 4 things, but I wanted to point them out to you. Okay? And I don't know how much you've done them in the past. I don't think you do. I don't think they're taught in pre-calculus. Is that correct? Okay.
I think I've done them before.
Okay. Have you done them in physics? Okay.
I haven't taken.
Yeah, I would say probably in physics you deal with coming up with that resultant. Maybe look at the angle and maybe look at the magnitude. Am I correct?
Yeah.
Okay. All right, so here's the idea behind vector-valued functions. Okay? So if you notice, I drew in 3 vectors here, correct? Okay? So the vector is going to have change as it moves along the x-axis. Let me back up. As time changes, the vectors change. So if you take a look here, whatever time I have, whatever that vector is, this vector is going to create this point right here. This vector is going to create this point right here. This vector is going to create this point right here. So time manipulates the vectors which change the x and y coordinates. So if I start here and time says, all right, do some, when t equals 0, I'm at this spot. When t equals 1, I'm at this spot. When t equals 2, I'm at this spot. I get these kind of continuous curves. Those are called vector value functions. Again, that's more than what you need to know. But I'm just giving you a kind of a bigger picture of what they are. So r of t is going to be a vector. It's going to have a value here. It's going to have a value here. That particular vector will go over to the right or over to the left and up and down and create a point, an x value and a y value. We're going to have something called the first derivative of a vector. And how do you do that? You just take the derivative of the functions that are inside that vector. The second derivative, you take the second derivative of the functions that are in that vector. You're going to look and see at the examples that I've done, and you'll say, hey, we've already done these kind of problems already. we just are adding to them. This is where we bring in some physics, velocity and acceleration. So the velocity function is the first derivative of this vector valued function. And I just take the first derivative of the x component and the y component, the I component and the j component. Acceleration is going to be the second derivative. Speed is the magnitude of the velocity vector. And it's computed in this fashion. Take a look at it. It looks like the Pythagorean theorem. The total distance traveled on a curve is computed this way. We have done these kind of problems before. All right? Can I switch to the next page?
Yes.
Why is speed different than velocity?
Speed is, velocity has direction. Speed is the absolute value. It's always positive. It's the absolute value of the velocity function. Okay. Okay, so this is some review. dy dx is the slope of the tangent line on a curve. It's the slope of the path of a particle traveling along the curve. It's the rate of change of y with respect to x. And those are just some review things of, so to give you some ideas of what you're trying to compute. The second derivative is the rate of change of the slope of the curve with respect to x. dx dt is the rate at which the x-coordinate is changing, or it is the velocity of the particle in the horizontal direction. Y prime of t is the rate in which the y-coordinate is changing, or the velocity of the particle in the vertical direction. The symbolism for the position function, or excuse me, for the position vector looks like this, which is the same as this. Xt I plus Yt j. And the reason I give you that is some problems write it that way instead of this way with these symbols. I threw in, somebody a couple of years ago asked, it might have been Jared Cost, is there a third derivative and a fourth derivative? And I said, I have no idea. So I looked it up. There is something called, if you take the third derivative, it's called the jerk vector. And if you take the fourth derivative, it's called the jounce vector. Okay? And so when you bounce a ball, it's the rate at which the elasticity of the ball changes.
That's really cool.
Which, again, something you won't need to know, but I thought it was interesting. All right, so if you compute this, this is the arc length of the curve, or the distance traveled by a particle from time A to time equals A to time equals B. All right, let's take a look at this. Let's see how well we can do these. Example 1. A particle moves along a plane at any time t, so the position of the particle is this. What's the velocity vector when t equals 1? Any ideas at all? Olivia?
3t squared plus 8t.
Okay, what is that? 3t squared plus 8t. What would that be?
That would be the derivative of the x. You forgot the squared.
So if I put 1 in there, I'd get what?
3 plus 8 is 11.
I get 11, right? Okay, so my velocity vector is going to start with 11. What else do I need to do? Figure out the y one, right? And Flora, what is the y one?
4t cubed minus 3t squared. So 1.
So my velocity vector when t equals 1 is this. That's an AP question. Or it could be written like this. If you can make your i's and j's correct. What about when t equals 2? Carter.
Okay, so you're gonna take the same derivatives on the first one.
Yep. What do you get when you put 2 in there?
Two, 44.
I didn't hear anything you said.
44.
44? I get 2 squared is 4 times 3
Plus 32.
plus 16,
Wait. Oh, yep, that. 28.
28. Okay. And what is that one? There's a 32. I bet you're using that one. 20? 20? So it's 28, 20. All right. Example 2. A particle moves in the xy plane so that any time where t is greater than or equal to 0, the particle is given by this. What's the magnitude of the vector? Well, the first thing I'm going to do is figure out what the vector is. So I get 2t plus 3. I suppose I should write this a little bit better. And the other one is 3t squared minus 6t. So when I put 1 in there, and when I put 1 in here, what will I get, Sean?
You'll get 5 for x and negative 3 for y.
So my vector is this. What's the magnitude or length of that vector?
It'll be the square root of 25 plus 9.
Is that 34?
Yeah.
So that's your length,
What?
the square root of 34. So it's going to be the square root of 5 squared plus negative 3 squared. Are you okay going from here to here? Okay. Okay, example 3. A particle moves in the xy plane so that x equals the square root of 3 minus 4 cosine of t and y equals 1 minus 2 sine of t, where t is between 0 and 2 pi. The path of the particle intersects the x-axis twice. Write an expression that represents the distance traveled by the particle between the two x-intercepts. Do not evaluate. Jonathan, any ideas?
They say do not evaluate. I'm like, okay. I know. We wrote 2 sheets, and there was the like 8 questions, and one was like, you don't have to evaluate. Please, I'm like, I'll do this one.
I didn't hear anything you said. Where what? Correct? Where y is 0. We've been doing a lot of these. So what are those two spots?
Pi over 6.
5/6 and
5 pi over 6.
5 pi over 6. Okay? So now what we want to do is come up with an expression for the distance traveled. So you need to look back on your notes. How do you compute the distance traveled? Jaden? I'll give you a hint. It's an integral.
Is it the integral from? You want just to do the?
Yeah, tell me what you think should be here.
So integral of pi over 6 to 5 pi over 6.
Okay?
Square root.
Square root.
DT.
dt, I bet, right here.
DT.
Okay?
Negative, or I mean,
What are you trying to do?
get the derivative of x.
Okay, so the derivative, first derivative of x of t. Well, that'll be gone, correct?
Correct.
So what's the derivative of cosine?
Negative sign.
So you got negative 4 times negative sine. What does that become?
4 sine.
4 sine t. So I'm going to put 4 sine t in here. What am I going to do to it?
Square it.
Okay, is there a plus sign then that's next?
Yes. Yes, there is.
Okay, what do I need to do next?
Square y, or I mean, not the derivative of y, which would be negative 2 cosine.
And so I'm going to have a negative 2 cosine t, and I'm going to square that, correct?
Correct.
And I don't have to evaluate it, I just got to write this integral. I'm done. I'm liking this problem.
I love questions you don't do.
What?
I love it when it says set out but do not evaluate.
Yeah, usually that's on a no
Twice.
calculator part.
I love it.
All right, example 4. Is that all right that I keep doing the examples? Okay. An object is moving along a curve xy plane. Here's the position vector. You know it's a position vector because it has these exaggerated less than and greater than symbols, where the x derivative is this, the y derivative with respect to time is this. It says at time equals 2, the object is at the position 1, 4. Find the acceleration vector for the particle at 2. Rachel, you got an idea what to do?
You take the derivative of dx dt.
Okay. And what would that be?
Cosine t cubed times 3t squared.
And if I plug in 1, or excuse me, not 1, if I plug in 2 in here, what do I get? And you don't have to go to your calculator.
Yeah, 8.
I have the cosine of 8. And what do I have in front? Maybe you said it.
Yeah. 12.
Did you say 12?
Yeah.
Okay, sorry. And so then you're going to do this one, correct? Okay, so d squared dt squared equals what?
2t times negative sign.
So I can make it a negative 2t sine of t squared. Are you okay with that?
Yeah.
And when I plug in 2 into there, what do I get?
Negative 4 sine 4.
And so I just needed to get it in the vector form. And you could put that in your calculator and figure out what those values are if you wanted to, right? Okay. So, equation of a tangent line. What two things do we need?
Point and slope.
We need point, slope. Which should we do first? Which would be the most advantageous to do? What kind of form is the slope if I want a tangent line? Yeah, it's rectangular, I agree. So the slope of the tangent line is d what over d what? dy over dx. How do I get that? Yes, ma'am.
Would you take the derivative of dy? It's like dy dt over dx dt?
Do I have dy dt? And do I have dx dt?
Yeah.
So what is dy dt? It's cosine t squared
Yep.
over sine of t cubed. And we want it at t, so we get the cosine of 4 over the cosine of 8. Excuse me, sorry, the sine of 8. And we could figure that out on a calculator, right? How do we get the point?
It's given.
Hmm?
It's given.
Oh, it's given, right here.
Yep.
Well, that's nice. So that means the equation of our...
Wait, no. Oh, yeah. Sorry.
Are you okay with that? Okay. So we have the cosine of 4 over the sine of 8 times x minus 1 plus 4.
Wait, what? Oh.
Okay. All right. Speed of the vector. Speed of the vector is also the length of the vector, of the velocity vector. Do I have the velocity vector anywhere?
Is speed and magnitude the same thing?
Yes. But what? Do I have the velocity vector? Do I have the components for the velocity vector?
You have the equations to find them.
Pardon?
You have the two equations you need to find.
Okay, what are the two equations?
Sine of t squared and the cosine of t, or sine of t cubed and the cosine of t squared.
So the sine of 8, would you agree? And the cosine of 4? Correct? Because if this is the velocity, this needs to be x prime of t, or dx dt, and this needs to be y prime of t, or dy, or dy dt. So now, what's my speed? And Haley was right when she says, is it the same as the magnitude of this vector? It is. So how do I figure that out?
I read all this. It's like
Square root of what?
I literally didn't know.
Sine of 8 squared plus cosine of 4 squared. Okay, seem doable, especially since we had talked about parametric equations before. Very, very similar, aren't they? The only difference to me is this vector notation. Okay? Position function. Integrate what?
dx dt and dy dt.
Yeah, how do I do that? What does it tell you to do to integrate it? I got to integrate both functions separately, correct?
Yeah.
Am I right?
Where is this?
I think it says it, right here. RT is the position function. I'm gonna write this down here, position. Then if you want to, or if you want to get the position function,
Oh, okay.
I'd have to integrate these, correct? Right? So I'm gonna have to integrate,
Oh, class is over.
class is over. All right, no bell. We'll finish this up tomorrow.